In Chapter 12, we're going to look at some different curves, such as parametric curves, polar curves, and we're going to look at conic sections. This is going to prepare us for the later sections in Calculus 3, and also you'll see these again in Calculus 4. So the first thing we're going to look at is we're going to look at our parametric equations. So parametric equations are just equations that are written in terms of a parameter, usually t, and for practical purposes t usually stands for time. So for any value of t, we'll get corresponding x and y coordinates. What this is useful for is to find the position of an object at any time t. So when we talk about the way a curve is generated, that is what we call forward or positive orientation. So again, it's the direction that the curve is generated as t increases. In example 1, we're going to graph the parametric equation, and here we're given that our t values are greater than or equal to 0. So notice that x and y are separate equations written with respect to t. So what I'm going to do is I'm just going to make a table of values where for every t value I'll have corresponding x and y values. Notice that you can graph parametric equations on your TI-83 or TI-84 graphing calculator. In your calculator, choose mode and then change from function to parametric. You can also graph these using an online graphing program such as Desmos Calculator. So since our t values start at 0, that will be the first t value that I put in. When t is equal to 0, my x value is 1 and my y value is 0. So it's going to pass through 1, 0. When t is 1, I have an x value of 0 and a y value of -1. So this is going to pass through the point 0, -1. So you can kind of see that if we started at the point 1, 0 and then we go to the point 0, -1, that this curve looks like it's going to be generated downward as the t values get larger and larger and larger. So let's try another one. When t is 2, x is -1, y is -4. So it's going to pass through -1, 1, 2, 3, -4. So again, this looks like it's going downward. Let's just do one more. When t is 3, x is -2 and y is -9. So -2, -9, and it's still going downward. Okay, the problem is I don't know if this is going to keep going in the same direction. My guess is that it will. Because when I look at these x and y values, as t gets larger and larger and larger, the x values are going to get smaller and smaller, and so will the corresponding y values. So let's talk about how we label our graph. Well, we typically will label it with the t values. So when t is equal to 0, we're at our first point. When t is equal to 1, we're at the next point, and so on. And here we have t is equal to 2, t is equal to 3. And sometimes people will also write in the corresponding x and y coordinates as well. So we might in parentheses put in the point 1, 0, parentheses put in 0, -1, and so on. Something else we do with our graphs, if they're generated in a direction, is we'll put in arrows to indicate the direction that the graph is generated in. So the question comes up, If I keep adding in these t values, is this graph going to continue to go downward? Because it seems like its positive orientation is downward and maybe to the left. So on your MyLab, it may ask you to choose a direction when you're graphing parametric equation. So downward to me is sufficient, but they also may have you do end to the left. So one way that we can verify that this is true without using a graphing utility is to eliminate the parameter t and write an equation with only x and y. And then maybe it'll be an equation that we recognize. So right now I'm going to eliminate t. The most efficient way to do this is to take one of the equations, x or y, and see if you can solve it for your t value. Once you've done that, you can substitute that into the other equation. So when I look at my equation, I notice that x is equal to 1 minus t. So that seems an easy equation to solve for t. The y value has a t squared, so I know that if I solve for t, I'm going to get a plus minus when I square root both sides. So here I'll have t is equal to 1 minus x. And now I can go ahead and substitute this into the y equation. So y is going to be negative on the outside of the parentheses 1 minus x quantity squared. So this looks like a parabola. It looks like a parabola opening downward. I can see that the vertex is at 1, 0. Because this is written in the vertex form, but if you, almost in the vertex form, but if you don't see that, you can always just multiply this whole thing out, and eventually you'll get negative x squared plus 2x minus 1. So you can see that it's a parabola opening downward, and that's all I need to conclude that my graph will continue on. So with parametric equations, if you're not given your t value, and in our case our t value was greater than or equal to 0, if you're not given that, then you can assume that it's for all t values from negative to positive infinity. Let's add some more concepts. Oftentimes we'll be graphing circles. What's really nice with circles is they have a generic form where the x value is going to be equal to some x sub 0 or x naught plus a times cosine of bt. And the y value can be written as y equal to y sub 0 or y naught plus a sine of bt. Now this is not the only way that we can write circles parametrically. It's just the most common way. Now, if your b value, the coefficient on the t, is positive, then the circle is generated in a counterclockwise direction. Okay, so that's its positive orientation, counterclockwise. So just as a review, remember that when we're dealing with circles, the general form, if our radius is the absolute value of a, and the center is x sub 0, y sub 0, the general form would be x minus x sub 0 squared plus y minus y sub 0 squared equal to a squared. So that might be helpful when you're eliminating your parameter t. Let's look at example 2. So we're supposed to eliminate the parameter to describe our circle, or it could be an arc. It might not be a complete circle, given those t values. And then we're going to state the center, the radius, and the positive orientation. So here notice that my x value is 2 plus sine t, y is equal to cosine of t. Well, that's interesting. The general form has x as cosine, y as sine. but that doesn't matter. So if you exchange sine and cosine, what happens is your circle will be generated in the clockwise direction. Exchanging sine cosine changes the direction that your circle is generated in. Another way that you can change the direction that the circle is generated in is changing your b value. If your b value is positive, change it to a negative. So the interesting thing about these parametric curves is that they're not unique. There's infinitely many parametric equations to describe the same curve. So if I were to eliminate the parameter, I could use the equation without the parameter. Here notice that my x sub 0 is going to be 2. And I have no y sub 0, so here the y sub 0 is just 0, which means our center is the point 2, 0. Again, you can always graph this just to verify. Also notice that the coefficient on t is 1. Okay? So that also means that my b value is equal to 1. Now when we look at the radius, we're looking at the coefficient on sine and cosine. And here, that would be our a value. Our a value is 1. So that means my radius is 1. And the question is, what is the direction that it's being generated in? Well, because we exchanged the sine and the cosine in the generic form, we've changed the direction. So this is actually being generated clockwise. So if your b value is positive and you exchange sine cosine, it changes the direction. Again, you can verify this by a calculator or a graphing device. So the next question is, what is the equation without the parameter? And that would just be x minus 2 squared plus y minus 0 squared, which is just y squared, equal to our radius squared, which is 1. All right, so is this a complete circle? Now we have to look at our t values. Our t values are only going from 0 to pi. If this were a complete circle, then it should go from 0 to 2 pi. So just to get an idea of what this looks like, I'm going to go ahead and sketch a graph. Okay. When t is equal to 0, sine of t is going to be 0. So we're at the point 2, cosine of t is 1. We're at the point 2, 1. Okay, so let's go ahead and graph that point. And maybe I would like to make just a short table of values where we have our t values, corresponding x values and y values. Again, this is if you're doing it by hand. So we started at t is equal to 0, which gave us an x value of 2 and a y value of 1. So I'm going to go 1, 2, and 1. I'm going to choose pi over 2 for my next t value, because remember, I'm putting this into sine cosine. I want to choose some nice values. So at pi over 2, sine is 1, so my x value is 3, but my y value is going to be cosine of pi over 2, which is 0. So this is going to pass through the point 0.30. And this graph is making sense to me because it's being generated clockwise. Now I'm going to look at the last point, pi, where my t-value's n. Sine of pi is 0, so this is going to be the point 2. Cosine of pi is -1. So we're going to be down at 2, -1. This is just a sketch, just so I can get an idea, right, of how this is being generated. Okay, so this is being generated in the clockwise direction. However, it's not a complete circle. It's just an arc or a half circle. Okay, so we found our center, our radius, we found the direction that it's being generated in, and we also eliminated our parameter. So just remember, this is not unique. There's infinitely many ways that we can describe circles. Which brings us to example 3. In our previous examples, we were actually given a parametric equation. But what if you had to come up with a parametric equation? If we had to find the parametric equation, again, this is not unique, of a circle, so we know it's going to be a circle, and we know it's going to be centered at 0, 3. We also have our radius of 4, and we know that it's generated clockwise, not counterclockwise. This is generated clockwise. Sorry, I can't speak. So since the center is the point 0, 3, that would be my x sub 0, y sub 0. And the radius of 4, that's going to be my a. Remember, it's the absolute value of a. So I'm going to look at the general form that x sub 0 is, or x is equal to x sub 0 plus a cosine of b of t, and y equal to y sub 0 plus a sine of bt. Since it's generated clockwise, I have two choices. Well, actually I have more than that, but the two most common things I could do is I could exchange the cosine and the sine, or I could make sure that my b value is negative. So I'm going to choose that second technique, because we had already exchanged sine cosine in the previous example. So I know my x sub 0 is 0. So my x value is going to be, and my a, the absolute value of a is 4. So I'm going to choose positive 4. Notice I could have also chosen negative 4 for my a value, and that again would change the way the graph is generated. So there's a lot of options here, which is why your parametric form is not unique. I'm going to leave cosine the way it is, and I'm going to replace the b with a negative. So that would change the direction from counterclockwise to clockwise. Y is going to be equal to 3 plus 4 sine of negative t. And since this is a complete circle, I'm going to state my t values. So remember, you should always be stating your t values. So I'm going to state my t values as 0 to 2 pi. Remember, this is not unique. Also recall that cosine is an even function and sine is an odd function. So we can simplify this further by just getting rid of the negative in the argument for cosine and moving the negative out in front of the 4 with the argument on sine. But I'm just going to leave it this way. And make a note that this is not unique. So I could have also just exchanged the sine and the cosine. and written my x value as 4 sine of, and leave it as a positive t, right? Y as 3 plus 4 cosine of positive t. Exchanging sine cosine would have changed the direction, but keep the b value positive. Right. Something else that might come up is, we need to have our t values, is we could also change our b value, and we could still generate the same circle. I can do this infinitely, by the way. So what if x was equal to 4 sine of 2t instead of t, and y is equal to 3 plus 4 cosine of 2t? Well, that just means that since I'm multiplying t by 2, the t values are growing at a faster rate. So if I were to take my original interval from 0 to 2 pi and divide it by 2, I'll get a complete circle for t values from 0 to pi. Okay, so you can verify that if you put these equations into your graphing utility, that it all generates the exact same circle. It may have a different starting point on the graph, okay, but it should all be generated clockwise, and you should get a complete circle. So you see, these are just 3 ways to represent this circle. The more conditions you have, the less choices you have for your parametric representation. So let's go on to some more examples. In example 4, we have an application problem. So a bicycle is moving with a constant speed, and this bicycle is moving in the clockwise direction around a circular track. So we know it's going to be a circle. We have the radius as 600 meters. The bicycle will complete 1 lap in 1.4 minutes. So that would be our t value. We can go from 0 to 1.4 minutes. We want to find a parametric equation that models the path of the bicycle. Well, it is a circular track, and we have the radius. We don't have the center, but you can choose any center you want. Because we're not given a center, we can choose where that circle is in our coordinate system. So why don't we just choose the simplest center, which would be 0, 0. So again, we're choosing where we're going to graph this track in our coordinate system. It's up to us. So if I choose a center of 0, 0, and I have my t values, I also have that the radius is 600, so I also have the absolute value of a is equal to 600. And if I use the generic formula and just switch, because it is going to be going clockwise, switch sine cosine, then I could change the direction from counterclockwise to clockwise. So I think I'm going to do that. I'm going to use x sub 0 plus a cosine of bt. So that was our original. Y equal to y sub 0 plus a sine of bt. I think what I'm going to do is I'm just going to exchange the cosine and the sine so that I can exchange the direction. My x sub 0 is 0. So my x coordinate is going to be, a here is going to be 600. So I'm going to use 600 sine of bt. Now I'm leaving the b the way it is because my t values are not going from 0 to 2 pi, which would be the usual full circle. They're going from 0 to 1.4. So to adjust to that for that. I have to solve for that b value. My y value is going to be 600 cosine of b of t. So remember, our t values are not 0 to 2 pi. So since I know that 1 lap is 2 pi, okay, so maybe I'll write that down, that 1 lap is 2 pi. I know that bt, which is going to go from 0 to 2 pi, would give me 1 lap. And I know what t is at 1 lap. T is 1.4. So this is simply dividing the usual 2 pi by the 1.4 to get my b value. So that's going to give me, if I just move the decimal over, it's going to give me 20 pi over 14, which would reduce to 10, and I'll leave it as an exact answer instead of an approximation, 10 pi over 7. Okay, so one way that I could write this is x equal to 600 sine of 10 pi over 7t, y equals 600 cosine of 10 pi over 7t, with t values from 0 to 1.4. Again, this is not unique. If I had chosen to keep my b value as 1, that would have meant I'd have to adjust these t values. But the t values were given to me, so I didn't want to adjust them. We can verify that this gives a circle generated in the clockwise direction for t values from 0 to 1.4. Again, remember, this is not unique. We're going to move on from circles, and we're going to look at another type of parametric equation that comes up a lot, and that would be lines. So the parametric equation of a line that's passing through some point x sub 0, y sub 0, and with a slope of b over a, is going to be x equal to x sub 0 plus at, y equal to y sub 0 plus bt. Okay, again, this is just a general form. It is not the only form. And I'm fine with you using any form you wish, as long as it makes sense and it describes the curve. Okay. In example 5, we want to find the slope and a point on the line, and then we want to graph it. Okay. So that's pretty basic. If we choose, we can just come up with a table of values, but why don't we just use the general form? If I look at the general form of my line, I know that x is equal to x sub 0 plus at. Looking at the x value, that tells me that x sub 0 is equal to 2 and a is equal to -3. Looking at the general form y equal to y sub 0 plus bt, I can see that my y sub 0 is equal to 3 and b is equal to 1, which means my slope, and we usually use m for our slope, is going to be equal to b over a, 1 over -3. And the point that it's going to be passing through is our x sub 0, y sub 0, which would be the point 2, 3. So if we were to graph this, we would start at the point 2, 3, and then we would use our slope to count. Okay. So if I go 1 for y value, that's up 1, and then the negative 3 means x values to the left, 1, 2, 3. And I have this piece of my line. But remember, we can also move our negative around. I could use negative 1 over positive 3, which would mean from this point I would go down 1 and to the right 3. My line is really sad. It's not straight at all. So since the t values were not stated, we can assume that our t values are going to go from negative infinity to positive infinity. And they have to, because we're looking at a line which goes on infinitely in both directions. So the question is, how is this generated? Well, we can simply put in a t value of 0, right? Make our table of values and see what happens. So if t is equal to 0 in my parametric equation, I'm passing through the point 2, 3. If t is equal to 1, then I'm going to be going in the upward direction. So if t is equal to 1, we have an x value of negative 1, and we have a y value of 4. So it looks like this is generated upward and to the left. In the previous example, we were given a parametric equation, and again, now we're going to come up with a parametric equation. Since it's going to be a line, but this time it says a line segment, so it's not the whole line, which means that our t values are not going to go from negative to positive infinity. Since it's a line segment, and it's going to be between these 2 points, I have to figure out what my t values are. But first, what I'm going to do is I'm going to look at the general form of a line, which would be x equal to x naught, or x sub 0, plus at, y equal to y sub 0, plus bt. And then here I can choose either point that's given to me as my starting point. This just says to find a line segment between the 2 points. It doesn't say that you're starting at 2.2, 5 and ending at negative 1, 3. So I don't really have a direction. I'm not given a direction. So it's my choice. So I am just going to let my x sub 0, y sub 0 be the point 2, 5. And again, you could have chosen your x sub 0, y sub 0 to be the negative 1, 3, since we weren't given a direction. That will give me x equal to 2 plus at, y equal to 5 plus bt. So now I have to figure out what a and b are. I'm going to compute the slope. I have 2 points. I'm just doing the y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And it doesn't really, it doesn't really matter which point you start with, since we don't have a direction that it's generated in. But I'm just going to do 3 minus 5 over negative 1 minus 2. So that gives me a slope of negative 2 over negative 3. So I could use that a is negative, or b is negative 2, and a is negative 3. However, I could also reduce this or simplify this as positive 2 over positive 3. So I could also choose A to be 3 and B to be positive 2. It really doesn't matter because we weren't given the direction that the line segment was generated in. Now, if you were given a direction, then you would have to be careful. My x is going to be 2 plus, I'll choose the positive 2 over positive 3. So I'll choose my A to be 3. And I'll choose my B to be the positive 2. So y is equal to 5 plus 2t. Now I have to figure out what my t values are. So if t is equal to 0, I'm at the point 2, 5. But if t is equal to 1, I am not at the point -1, 3. Okay. So how do I figure that out? Well, I have this equation. I'm trying to figure out that t value, and I know my x value is going to be -1 and my y value is going to be 3. So if I simply put in -1 for x and 3 for y in my equation, then I can solve for my t value. Now I don't have to do them both, but I am going to do them both because I better get the same t value, right? So if I do solve this, I'll get that t is equal to -1 here, because I'm going to minus 2 and divide by 3. So I should get -1 on the other side as well, and I do. If I subtract 5 and divide by 2, I get -1. So that tells me that my t values are going to go from -1 to 0. Remember, this is not unique. So what if you wanted your t values to start at 0? Let's say t does represent time, and we're looking at an object and its position through time. Well, it doesn't make sense for our t values to be negative. So in that case, what we're going to do is we're going to look back at the slope. Remember, I had two choices. I had a -2 over -3 or a positive 2 over positive 3. Now, if I choose b to be the -2 and a to be the negative t, that would change the way my curve is generated. So I could choose x to be 2 minus 3t, y to be 5 minus 2t. And then you can verify that the t values would go from 0 to 1. Again, not unique, infinitely many choices. If I take that slope and I multiply or divide top and bottom by some non-zero number, then that would change this completely. But it would still represent the graph of a line passing through the same points. But it'll pass through those points for different t values. We're not just restricted to circles and lines. Those are just the most common. So some other curves that may come up, well, let's say that you wanted to find the parametric representation of a parabola. And we have the equation as y equal to 4 minus x squared. So we have to add our parameter t. Again, there's more than one way to do this, but what I do is I look at my interval if it's given to me, and this interval says the x values are going to go from 0 to 2. So remember, our idea is to break this equation up into an x value written in terms of t and a y value written in terms of t. So since my interval goes from 0 to 2 and it's an x value, I am just going to let x equal t. When I do that, then I get the t values are going from 0 to 2. And I can simply replace x with t in my equation to get my y values. Typically, when you're looking at a parabola, you want to replace whatever is squared with the variable t. So the more complicated piece with your variable t. And I had the added benefit that I was also given this inequality that had x in it. Sometimes that's not given. So if the interval or the inequality is not given, and it's something that has a variable squared, but the other variable is not squared, then choose your t value to be equal to whatever's squared, or cubed, or whatever is the more complicated piece. And try that. But just remember that this is not unique. We've been looking at a lot of algebra. And we're going to do one last example with line segments, because this will come up later on in Calculus 3 and 4. And then we'll move on to a calculus concept, which would be our derivatives. Example 8, we want to find a set of parametric equations that represent the path from. So that implies a direction. I'm going to start at the point 1, 3, and I'm going to go to the point -5, 4. And then from -5, 4, I'm going to go to the point 0, 7. So in this particular example, I'm actually given a direction. I want to get a better idea of what's going on here. So I'm going to go ahead and just graph these points and get an idea of what this looks like. Okay. I'm also given that my t values are going from 0 to 2, so I always have to keep that in mind as well, that when I do write my parametric equation, I have to have t values between 0 and 2. So this is a case where you have a lot of criteria that you have to meet, so that's going to reduce the choices you have when you write your parametric equation. So if I start at the point 1, 3, I'm just going to do a sketch, so it's probably going to be about here somewhere. And then I'm going to go to -5, 4, and it's going to be traveling to the left. From -5, 4, I'm going to go to 0, 7. Oh, so probably have to make this a little bit longer. And again, I'm given a direction, so I have to be careful with that. So I'm starting at the point 1, 3. Oops, sorry. And then I'm going to the point -5, 4. So that's going to be the first parametric representation. Now, since these are two different line segments and they're going in two different directions, I'm actually going to have two sets of parametric equations to describe this path. The first path is going to go from t is equal to 0 to some t value between 0 and 2. And then for the second leg of my journey, I'm going to take that ending t value and then go to a t value of 2. So I'm going to choose my starting point 1, 3 to be the x sub 0, y sub 0. And then I'll end up at -5, 4. I'm going to use the general parametric form of the equation of a line segment, or a line. I need my slope. So in this case, since I'm starting at 1, 3 and ending at -5, 4, I'm going to do ending minus starting point. So it's going to be 4 minus 3 over -5 minus 1, which would give me a slope of +1 over a -6. And I'm going to keep the negative in the bottom. So my b is going to be 1, and my a is going to be -6. X is going to be equal to 1 minus 6t. Y is going to be equal to 3 plus t. So now let's think about our t values. When t is equal to 0, I'm at the point 1, 3. So that's good. When am I going to be at the point -5, 4? For what t value? I want to make sure that that t value is between 0 and 2, right? So if I put in -5 for x, and I solve for t, then I get -6 divided by -6, I get 1. Now if I put t is equal to 1 in the y equation, I get the point 4. So when t is equal to 1, I'm at the point -5, 4. So that's good. From 0 to 1, I'm going from the point 1, 3 to the point -5, 4. Now's the tricky part. I need to go from the point -5, 4 to the point 0, 7. I can't simply use x sub 0, -5, y sub 0, 4, because that won't give me the correct t value. So before figuring out what my x sub 0 and y sub 0 are, I'm going to go ahead and figure out my slope first, because those values are given to me. I'm starting at -5, 4, I'm ending at 0, 7, so my slope is going to be 7 minus 4 over 0 minus -5, which is going to give me a +3, over a +5. So this is my b over a. So this is where I'm at so far. I know that my x value is going to be x sub 0. My a value is a +5, so it's going to be plus 5t. My y value is y sub 0. B is a +3, so plus 3t. So I have to figure out what x sub 0, y sub 0 I'm going to use that'll give me my correct t values. Okay. So remember, I'm starting at the point -5, 4. So if I put in -5 for x, and my starting t value is going to be 1, because that's where I ended previously. So this is going to be -5 equal x sub 0 plus 5. And solving for my x sub 0, I get -10. My y value is going to be 4. And this is when t is equal to 1, so I have a +3. If I minus 3 from both sides, I get y sub 0 is 1. Okay? So when you have a path with many line segments, the first part of your path, you can always take your x sub 0, y sub 0 to be your starting point, because that happens when t is equal to 0. But as your t changes, you have to change that starting point. So this is good. I have my x sub 0, y sub 0, and I also have my a and my b. So now I have x equal to -10 plus 5t, y equal to 1 plus 3t. And then we'll just verify, this starts at 1, doesn't it? How do I know it ends at 2? Well, we could algebraically figure that out as we did before, or I could simply substitute in 2 for t and see if I get to the point 0, 7. So just to verify, if I put in 2 for t, this is negative 10 plus 10, and I'm at 0, that checks out. If I put in 2 for t, I get 1 plus 6, so y is equal to 7, and I'm at the point 0, 7. All right. So enough with parametric equations and finding their equations. Let's look at a calculus application, which would be a derivative. So how do we find the derivative of a parametric equation? It happens to be extremely simple. To find the derivative of y with respect to x, all you have to do is take the derivative of each piece separately, and it's always y over x, right? It's slope, it's a rate of change. So take the derivative of y with respect to t and the derivative of x with respect to t, and you're done. So super simple. Example 9, we want to find the derivative for our curve, but the curve is given parametrically. Okay? So instead of getting rid of the parameter t and computing the derivative, I can just use this formula to find the derivative. dy dx is simply equal to the derivative of y with respect to t would be 3, if I could write 3 over 2 times the square root of t. And the derivative of x with respect to t is just 1. So our derivative is simply 3 over 2 square root of t. So we found the derivative. And the next part says determine if there is any point where the curve has a horizontal or vertical tangent line. If we have a horizontal tangent line, that implies that our slope is equal to 0, or our derivative is equal to 0. So if I set my derivative equal to 0 and I solve this equation, I get 3 equal to 0, which is not true. Since there's no solution, there is no horizontal tangent line. Okay. So now we have vertical tangent lines where the derivative is undefined. So that means 3 over 2 square root of t is undefined. So I could see that the variable t is in the denominator, and this fraction is only undefined when t is equal to 0, because then I'll get 3 over 0, which is undefined. So at what point, because we're supposed to find the point where we have a vertical tangent line, well, put in t is equal to 0 into our parametric equation, and we get the point 1, 0. So there's a vertical tangent line at 1, 0 when t is equal to 0. So we'll write that out. Vertical tangent line at 1, 0 for t equal to 0. Let's go to another example. In this example 10, it says find an equation of the line tangent to the curve for the given value of t. So I'm given a parametric equation. X is equal to t squared minus 4, y is equal to t cubed minus t. And I want to find the equation of the tangent line when t is equal to 3. So remember, this is an equation of a line. We're going to need a point, we're going to need a slope. So the equation of a line is y minus y sub 1 equal to mx minus x sub 1. So I need my x sub 1, y sub 1. If I just put in t equal to 3 into my x and my y values, then I get the point 5. 9 squared minus 4 is 5. And then 5 to the third is 125 minus, 3, sorry. 3 to the third is 27 minus 3, 24. So I have my point. I need my slope. And that comes from our derivative. So we're going to compute the derivative, and we're going to evaluate this derivative when t is equal to 3. So our derivative is the derivative of y with respect to t would be 3t squared minus 1. The derivative of x with respect to t is just 2t. So when we evaluate this for t equal to 3, that gives us 26 over 6, or reduce 13 over 3. Now we'll put all of that together to write the equation of our tangent line as y minus 24 equal to 13 over 3 x minus 5. And that's fine.